Yesterday we went over velocity versus time graphs. And one of the things that we can see and calculate from a velocity versus time graph is the acceleration of the object. So if I had, okay, a velocity versus time graph that looked like this, what's that object doing? Accelerating in a negative direction. Okay, given the steepness of the line and the lack of scale on my axes, okay, we could at least infer that that acceleration is fairly large. Okay, given the slope of the line represents the acceleration of the object. Okay, and we figured that out because we know when calculating slope, you're taking the change in y and dividing by the change in x. Well, on the y-axis are our velocities, and on the x-axis is time, and that formula is the one we learned last year in Science 10 that calculates acceleration. Today, we are going to learn 4 more. Okay? So, there's more acceleration formulas in Physics 20 than there were in Science 10. They're not any harder or any easier to use, it's just algebra. Okay? So it's nothing that you guys can't handle. All right, so we have to understand what accelerated motion is. If you recall, I've said several times now that in physics we don't use the term decelerate. Okay? Any change in velocity is an acceleration. That is the definition of acceleration. Any change in velocity over time. We need to learn the relationship between change in velocity, distance, time, and acceleration. And we've kind of already looked at that in terms of what does it mean? Well, an accelerating object is going to obviously have a change in velocity, either negative like this or positive like this. From a position versus time perspective, okay, what that means is a positive acceleration is that the distance traveled every second will be larger than the second before. Okay, that's the relationship between acceleration and distance. It's exponential. Right? You probably learned in math that this shape is an exponential curve, type of parabola, okay, that is showing something increasing at a non-linear rate. Okay? The same is true if I have a position versus time graph with that shape. Is that a positive acceleration or a negative acceleration? It's negative. Okay? Slowing down, and in the case of that line, coming to a stop. All right, everybody okay with those ideas? All right, that's like point number 2. Understand what it means in terms of position when an object is accelerating, understand what it means in terms of velocity when an object is accelerating. All right, and then obviously be able to solve accelerated motion problems. We're going to spend the bulk of today going through examples for each of the new formulas that we're going to learn. All right. So, as we said, the definition of acceleration is that whenever the velocity of an object is changing, we say the object is accelerating. Okay? The meaning of average acceleration can be illustrated by considering a plane during takeoff. Okay? Planes exhibit uniform acceleration better than cars. Okay? Because oftentimes people ask me, why don't you just say like a car pulling away from the light? What does a car have that a plane doesn't? No, there's still friction for a plane. I mean, it's got air resistance going over the wings. That's what makes the lift, right?
Just has to change gears.
It's got to change gears. Plane doesn't have to change gears. Okay, a plane, you just push the throttle forward and it's going to increase your velocity pretty uniformly. It's not perfect, but it's pretty uniform. Far better than it would be for a car, okay, whose velocity versus time graph, okay, would look something like this. First gear would be a short but very steep section of the graph, and then second gear, okay, is not as fast, and third gear not as fast, and fourth gear, and then fifth gear, okay, and if you have a sixth, well, the acceleration in sixth is pretty low, right? And if you've got something with a paddle shifter in 10 speeds, well, it's, you know, even more so, right? But it's not uniform because each gear pulls less than the gear before. That's why if you're passing somebody on a 2-lane road, okay, if you're in an automatic and you floor it, you can feel the transmission change gears, okay, to a lower gear that can produce greater acceleration. Or if you drive standard, okay, you downshift from 5th to 3rd, okay, or 5th to 4th, or 6th, 4th, or whatever it is for your manual transfers. Anybody drive a manual? I think that's like the highest number I've had in a long time, okay, because manual transmissions are going the way of the yo-yo. Almost nobody has them anymore. Okay. And interestingly enough, more and more cars now, especially hybrid cars, are going to a continuously variable or CVT transmission that doesn't have true gears. It's just constantly shifting the ratio, and it's not really a shift of gears. So the actual curve is a bit more uniform. Okay, or the acceleration curve is a little more linear than it is curved, simply because the transmission works differently. Okay, electric cars also have a much more linear acceleration curve. It does start to flatten near the end simply because of air resistance, not necessarily because there's any changing of gears. A Tesla doesn't change gears. Okay, it just goes. Actually, quite fast, surprisingly. Yeah. All right. So the first formula, the one we already know, is that acceleration is the change in velocity over time. So that would be VF minus VI over T. On your formula sheet, it's probably written like this. Okay, delta V over delta T. Delta always means final minus initial because delta stands for change. Okay, so anytime you see delta something, it's final that minus initial that. All right. Okay, everybody okay with that idea? Okay, so definition of acceleration, could that be a multiple choice question on a test? Totally. Okay. Okay, so let's say as our first example, this would be like a Science 10 super easy example. Okay, we have this plane that starts from rest. Is that a term we need to be familiar with? Yes. Yes. If something starts from rest, VI, or our initial velocity, is 0. What if it comes to rest? Then it's our final velocity. It's slowing down and coming to a stop. Okay, so if it comes to rest, VF is 0. It starts from rest, VI is 0. Rest always means stop. Okay, so this thing is starting from rest at time 0. The plane is going to accelerate down the runway, and after 29 seconds, we'll be moving at positive 72.2 meters per second. Okay? So we want to determine the average acceleration of the plane. All right, so acceleration is a vector quantity, okay? And it is the change in velocity divided by the change in time. We know all three of these things. So we just have to go 72.2 minus 0 divided by 29 seconds. Okay, everybody all right with that? Okay, so if we do that, we get 2.5 meters per second squared. How's that going to feel if you're in the plane?
Pretty darn fast.
Actually, it's not super fast. For a plane, it's not super fast. Okay, this would be about 1/4 of a G. Okay, right now you feel 1 G. Okay, that's the force you feel right now. Okay, because gravity is pulling you down. Okay, 1 G is normal gravity. Right, 2 Gs you feel twice as heavy as you normally do. 3 Gs, 3 times as heavy as normal. If you've seen any of the Top Gun Maverick footage, okay, where they're pulling like supposedly 9 Gs. Okay, yeah. Okay, they do a really good job incidentally in that movie of showing the G-forces because they actually put the actors in like the rear seat of 2 seat like fighter planes and pulled a lot of these maneuvers so you can actually see their faces peel back like this, okay, in the G-force because their face weighs 4 times more than it normally does because of the extreme G's they're pulling, okay, and they are not acting at that point. They are struggling to breathe, struggling to stay conscious, okay, because of the G-forces. This acceleration, not going to make you feel that way. Okay, you're going to feel gently pushed into your seat. Okay, because the seat's got to push you a little more than it would if you were stationary. Okay, and so you'll feel that push from behind that is making you go faster.
Isn't like 7 G's like almost lethal?
No, you can pull even more than, you can pull double-digit G's as long as it's not for an extended period of time.
Well, that's what I mean.
To a
it's
point.
like eventually, like I know you can get up to like almost 9 G's, but it has to be for like a split second, otherwise it becomes super lethal.
Not so much lethal. Like we can withstand, you know, a certain number of G's, even 9, 10 G's, 12 G's, as long as it's not for too long. The thing that makes G-force lethal is the fact that you black out and your plane crashes. Right? So if I'm a fighter pilot and I'm doing that 9G pull, and in one of the scenes, I don't want to spoil it for you, but one of them, right, nearly crashes because he blacks out. Okay, and that can happen. That can happen on a roller coaster. Okay, I've seen it. people just black out. There's just too much G-force, and it's over a short period of time. It's only 4 Gs, but it's only for a couple of seconds. So normally that's just kind of fun, okay? But if you pull 4 Gs for a fairly long period of time, the blood in your body is too heavy for your heart to pump it to your brain, okay? And that's what leads to the narrowing of your vision. You kind of, everything gets gray, you feel lightheaded and dizzy, and then you're unconscious, okay? And you're unconscious until your heart can recover, okay, and get oxygenated blood back to your brain.
Do like the G suits actually really do anything then?
Absolutely. So, if you ever had your blood pressure taken,
Yeah.
okay, the cuff they put on, the whole suit's like that, okay? And it's programmed with the computer in the plane, the gyro in the plane, so that when you start pulling G's, it starts inflating the cuffs everywhere, pushing blood into your brain, okay? Like squeezing it out of your extremities, pushing it to the brain to keep you conscious. It's not gonna work for, you know, a huge amount of time. It's gonna give you that extra second, 4 seconds or whatever, so that you're the one who blacks out and not the person shooting at you, right?
Yep.
Or the other way around, sorry. Yeah, the other person's the one that blacks out. And so you can survive longer, pull those G's for longer.
I have a question, like, so, cause, like, to use Top Gun as a reference, when he's pulling like 9 G's of force as he goes up, and then he drops down, like, cause he like blacks out. Would you still be pulling G's when you're going downwards?
No, what makes you pull the G's is that you're changing direction, especially in a climb. So if you're accelerating in a climb, you've got gravity pulling down, but you've got the seat pushing up, okay? And so that creates an even greater apparent force on you that is making it harder and harder, making you feel heavier and heavier. It's all, one of the worst places for it is coming out of a dive, this part right here, okay? Also tight turns can do the same thing, right? So anytime they're changing direction is when they're gonna feel that G-force. And there's a lot of training that goes into, you know, being able to withstand that. You or I, without training, 4 Gs for 10 seconds, we'd be out. Like, that's just it, okay? Those guys and ladies, they have incredible training that, you know, involves using the suit and using their muscles, their skeletal muscles, to squeeze blood as well, okay? So you'll hear, I think at one point in the movie, they're like, you know, you gotta, you know, clench your butt, clench your teeth, grunt, okay? All of those things are all things that they're trained to do that will force blood, especially the grunting. If you ever hear a fighter pilot, you can hear them do this, and it sounds like barking almost. And what they're doing is they're clenching the neck muscles and squeezing the carotid artery with their neck muscles, forcing blood to the brain, okay? In addition to what the heart can do, gives them a couple of extra seconds of being able to pull that force, right? Does that sort of make sense? So that's what this is nothing. 2.5 meters per second squared is nothing. You can feel that in a car. You can feel more than that in a car, okay? Most cars, their maximum cornering before they'll start to skid is somewhere around between 0.8 and 0.9 Gs, okay? So what that means is the force that you would feel from the window against your face, you know, in the passenger seat because the driver is crazy, and so you get thrown into the passenger seat and you're into the window like this, going around the corner, the force you feel on your head would be almost equal to what your head weighs, okay? That's what G-force kind of feels like, and that's the result of acceleration. We go over that a lot more in the circular motion. All right, so we're all familiar with that formula, okay? We've used that formula before, okay, back in Science 10. These are our other 4 formulas that we're gonna be using. They're on your formula sheet. You don't need to write them down, okay? So we've got the displacement equals VI times T plus 1/2 AT squared. Does anyone look familiar?
Yeah.
Yeah, because we went over it yesterday, okay? And we said that calculates the displacement by calculating the area under the line on a velocity versus time graph, okay? So if I have that on my velocity versus time graph, this is the bottom, how far I would go if I didn't accelerate, just average velocity times time, in this case initial velocity times time, and then this part is the triangle. It's the amount of displacement covered while the acceleration occurs. We add the 2 together and we get the total displacement. Okay, the next formula is doing this the other way, okay? So it's saying VF times T. So this is VF up here. If I go VF times T, what does that calculate? Yeah, it calculates the whole square or rectangle here, right? And then it says subtract 1/2 AT squared. Okay, this triangle and this triangle, are they the same?
Yes.
All right, so if I calculate the whole box and then subtract this triangle here, am I left with the same thing? They work the same way. If you have VF instead of VI, you use the other formula. Okay, and you can calculate it the same way. All right, VF squared equals VI squared plus 2AD. Not really a graphical one, okay, but we use it a lot in projectile motion when we know the maximum height a projectile can reach. Okay, because at its maximum height, how fast does it go? Zero, right? Okay, so we can use this one a lot when we're dealing with the vertical part of a projectile's motion because we know at its maximum height, its final velocity is zero, and it can help us to calculate what its maximum height or displacement, things like that. So we use that one a lot more when we're in projectiles. Okay, this one here, we don't use very much. We use it occasionally, okay, but it does require the acceleration to be uniform. Okay, in fact, the question must explicitly state that the acceleration is uniform if this one is going to apply, because what this one's really doing is this. It's really just average velocity times time. Okay? The reason the acceleration has to be uniform is so that when I go VF plus VI divided by 2, I'm actually getting a perfect triangle. Okay? And I'm getting that halfway point in the middle to actually get that average velocity. So, I mean, you look at this, it's an acceleration formula with no acceleration in it. Right? Acceleration is not part of it, but it's saying it could be used to calculate displacement if the velocity was changing uniformly. So it's really not a new formula, it's just a rewriting of one we already use. Okay? That's why it's not one we use very often. Okay, questions on the formulas? All right, so we're going to go over some examples here. Okay, so let's have you guys write this one down. This one will be pretty easy. Okay, so we have a hybrid car with an initial velocity of 10 meters per second east, accelerates at 3.0 meters per second squared east. Okay, how long will it take the car to acquire a final velocity of 25 meters per second east? Okay, so I'll give you a minute to get it copied down, and then we'll walk it through. If I give you an acceleration problem on a quiz or a test, okay, these are the steps I would expect you to follow. Each one would be worth a mark. Okay? First step, write down your givens. What are the numbers and values that the question gives you? Right? So first off, it says it has an initial velocity of 10 meters per second east. So VI is 10 meters per second east. And it accelerates at 3.0 meters per second squared east. Okay? How long will it take for the car to acquire its final velocity of 25 meters per second east? Okay, so that's one mark. Why do I give you a mark for writing down what you already are given? Because it helps you figure out which formula to use. You do, after all, have 5 acceleration formulas to choose from. Okay, so it's pretty simple to pick which formula you need. I just look for the formula that has those 4 things in it. Which one would it be?
Acceleration.
Which one? Which acceleration formula?
E equals VF subtract VI over T.
Right, the one from last year. A equals VF minus VI over T. Okay, I have all those parts except for T. Okay, that's what I'm going to solve for. So I just need to manipulate this. So sometimes I even give you a mark for picking the right formula. So write down the formula you're going to use. Okay, then you need to manipulate. All right, so if I want to get T by itself, I'm going to have to multiply both sides by T, and then divide both sides by A. Okay, and now I'm set up like this. VF minus VI over A. Okay, you'll get a mark for your manipulation. Right? Sometimes, if I'm feeling extraordinarily generous, I even give you a mark for plugging the numbers into the formula correctly. Not always, but sometimes. Okay, so we would be looking at 25 minus 10 divided by 3. Okay, so, and then my final answer, 15 divided by 3, is 5.0 seconds. 1 mark for your final answer. Okay? Elliot, thank you. Just close that door for me. Please and thank you. not for time, right? Time,
Oh,
time is scalar.
I thought about that.
Okay. All right, does everyone follow me on that one? Okay, so just to have a quick look at the manipulations for that formula. Okay, so A equals VF minus VI over T. So obviously we just looked at how to solve for T. Okay, we just basically switch A and T. All right, but what if I need to solve for VF? What would I move first?
You would add VI to A.
You'd multiply T.
Right. Okay, remember 3 rules of algebra. Right? If I want to move something, I do the opposite. What I do to one side, I do to the other. And I move what's not attached first. Okay? Right now, VI is attached to VF. Okay? So I can't move VI yet. I'm going to multiply both sides by T. Now I'm going to add VI. Okay, so let's just look at this formula and kind of understand why this manipulation makes sense. T times A equals the change in velocity. Everybody okay with that logic? Okay, so now I'm going to add VI over to this side. My initial velocity plus the change in velocity should equal the final velocity, yes? Okay, so if I'm walking it through kind of logically, that manipulation is not only mathematically, I like that term, I'm going to use that, mathematically logical, it's also logically logical. Okay, it makes sense that whatever I have to start with plus whatever I change it by should equal what I have at the end. Okay, everyone all right with that idea? Okay, so let's try this. Instead of solving for VF, now I want to solve for VI.
Don't you, when you do the same thing, when you have to add VI to the other side, and then you said you were looking at after for VI, so that when you do this, so you move VI to the other side, and then you take VF, subtract it, and then you subtract VI, or I guess you could just subtract VF and save it next.
There's 2 options here, actually. Okay. Some people just subtract VF over to the other side. Here's why I don't do it that way. If I subtract VF over here, I have T times A minus VF equals negative VI. I haven't gotten rid of that subtraction operation. Okay? It's still there. That's why I don't do it that way. I always forget that what I solved for was negative, which means when I'm done, I have east when I'm supposed to have west. Okay? And I always forget that, so I don't do it that way. Okay? What I do instead is I add VI over here, and then I subtract T times A. Now VI is positive. Okay? And here's why I do it that way, because it also logically makes sense to me. Whatever I finish with minus what I changed the velocity by should give me what I started with. Okay? It's like if you go to work and it's payday. Okay? You start out the day, you don't know how much money you had at the start of the day, but at the end of the day you have this much money. Okay? And you subtract from it what your paycheck says, and well, that's what you started the day with. Okay? Does that sort of make sense? Okay. So that's the manipulation for VI. That's all the manipulation you guys do. Okay. All right. Try those 2. The answers are right here. They used that formula. Okay? Give me 2 minutes to go over those 2. Okay? And we'll see how we do. So your units have to match, right? You can't divide kilometers per hour by meters per second squared. Okay? So your units have to match. Now, when we're converting kilometers per hour to meters per second, we have to do what's called a compound conversion. It doesn't come up often, but it's important to know how to do it. Okay? So if I have kilometers over hours, and I want to go to meters per second, I need to convert each one of these by multiplying by whatever conversion factor is necessary. So if I want to convert 1 kilometer to meters, how many meters is it? 1,000. So I've got to multiply my kilometer value by 1,000 meters. Okay, so now kilometers cancel. So whatever I had in kilometers per hour, I've multiplied by 1,000. Now I have meters per hour. How do I convert hours to seconds? Everybody says that. It's such a gut reaction. I love it. How many seconds in an hour? Oh, yeah, it's not 60, is it? 60 minutes in an hour. And 60 seconds in every one of those minutes. 3,600, yeah. Okay, all right, so in 1 hour, there are 3,600 seconds. All right, now my hours have canceled. So what I have is whatever was in kilometers per hour, I now have to multiply by 1,000 and divide by 3,600. Agreed? Or is there a quicker way? Is this also the same as saying 1 over 3.6? Okay, so whatever I have in kilometers per hour, I multiply by 1, which does absolutely nothing, and then I divide by, so take your kilometers per hour and divide by 3.6, and you got meters per second. Other way, multiply. Okay, so simple and quick conversion. Okay, kilometers per hour to meters per second, divide by 3.6, meters per second to kilometers per hour, multiply by 3.6. And then the answer's in kilometers per hour, so then you got to bring your answer back to kilometers per hour. But it's just multiply by 3.6 divided by 3.6.
So how do you know if you leave it in like kilometers per hour versus meters per second?
How do I know if I what, right?
Like at the end?
Yeah.
How do
It
you
would
know?
ask. Like,
Okay.
for me, if I really want a specific set of units, I would say in the question, solve in hours, solve in meters per second, okay, or something like that. If the question doesn't specify, I wouldn't convert back. I'd be like, you didn't say what units you want. I'm gonna take it easy and not convert again, leave it meters per second, okay? If you want something, you gotta ask specifically for it, right? All right, so for number 2, okay, we gotta convert this. So this is gonna be, so divide that by 3.6. What was it come out to?
5.5.
5.5, okay. And that was our initial, right? Right, so we're looking, so we'll get it in meters per second here. We're trying to find the maximum velocity, okay? And it says in kilometers per hour. So I'm gonna go A equals VF minus VI over T, multiply both sides by T, add VI to both sides. That's gonna solve for VF. So I'm gonna have 5.5 repeating, I think, right? Yeah, okay, plus 9.3 times 1.5, right? And that should give us our 70 kilometers per hour, but we'll get it in meters per second when we do this, so. Okay, so 19.5 meters per second, 70 kilometers per hour. Okay, everybody all right with that? Okay, so just be on the lookout for that. It doesn't happen very often, okay? Especially not with kilometers per hour and meters per second, but it happens more with, I give you meters per second and then I give you distance in kilometers. That's where you gotta watch it, okay? Because it's really easy to just plug in the kilometers and forget to change it to meters so it matches your meters per second. All right. Okay, so have you guys write this one down and then we'll figure out which formula we have to use and walk through how it works. Okay, so there's obviously an acceleration going on here, but they don't tell me what it is. In fact, how many numbers do they actually give me here?
2. Oh, technically 3.
3. One of them isn't written as a number, but it's still a number, right? Okay, so we've got cattle train traveling west at 16 meters per second. So VI is going to be 16 meters per second west. It's brought to rest. So VF is 0. Okay, in 8 seconds. Calculate the displacement. Assume uniform acceleration. What formula did I tell you that has to be present for if I'm going to use? The last one. And it's the one I have to use here because it's the only one I have this data set for. Okay, so I'm going to go D equals VF plus VI over 2 times T. All right, I just have to plug in my numbers. That's sweet. I like it when I don't have to manipulate stuff. Okay, it's obviously way easier. So D equals 0 plus 16 over 2, okay, times 8 seconds. 8 times 8 is 64 meters west. Okay. All right. What if I need to manipulate this equation? Let's say I need to manipulate for t. How do I get t by itself?
You divide that whole thing by 2.
Divide the whole thing by? If I do that, I can move t over, but it'll be on the bottom then, right? And I don't want to solve for t if it's on the bottom, because then I'm actually solving for 1 over t. I could do that, but it'd be a bit of a, I'd eventually get there. There's a quicker way.
You just.
How many of you right now are really wanting to just move everything in the brackets over all at once? Doesn't that seem like that'd be the easiest thing to do? Because it's the right thing to do.
Well, no, because you can't divide.
Why not?
But you can-
Divide 2.
Why not?
They're in brackets.
They're in brackets.
It's a whole different
Think
number.
order of operations. I have to do this first, don't I?
Yeah.
Then this is just x. X times t. Can I move x?
Yes.
Absolutely I can. There is nothing saying that I cannot do exactly what I just proposed to you. This is a number because I have to do that operation first when I follow order of operations. So to get t by itself,
It's just d divided by the order. See, I was gonna say that, but I was like, you can't divide.
I know you were.
A division 2.
But it felt wrong, even though you wanted to do it, right? It looks wrong. Oh, there's so many things, I can't move them all at once. Why not? They're in brackets. Okay? It's like, oh, there's all these boxes and this one big box. How can I move all those little boxes? Put them all in the big box and move the big box. Okay? Why not? That's what you're doing here. Okay? That's perfectly logical to do. Now, if there wasn't brackets, then I'd have to move it piecemeal. Okay? But it's all in brackets, so I can take it all together. Okay? Everyone all right with that? All right. Now, what if I want to solve for something that's in the brackets?
You have to take everything out of the brackets and
Before I can take the brackets off, what do I have to move?
T.
T, yeah. I got to get T over here. Okay, now this should make sense because, after all, this calculates average velocity. Average velocity is d over t, yes?
Yep.
Okay, now that t is gone, do I need the brackets anymore? No, those brackets were only there because t was there. So now, brackets are gone. I want to solve for either one of these. What do I do with the 2? And then I just subtract the other one over. Okay? And I got them by themselves. All there is to it. Okay? Don't overthink it. That's usually what happens. When people start to get confused, it's because they totally overthought something. All right. Questions there? Try those two. They use that formula. All right, so we have a hound that's running at 16 meters per second south. Okay, and it slows down uniformly to a velocity of 4 meters per second south. Okay, what's the displacement during the 4 seconds that it slows down? Okay, so formula I have to use is this one. D equals VF plus VI over 2 times T. All right, now for that first one, we're just plugging in the numbers. All right, so we've got 4 plus 16 over 2, okay, times 4. So 4 plus 16 is 20, over 2 is 10, times 4 is 40 meters south.
I plugged in the wrong numbers.
Okay, sometimes that happens. All right, how are we doing with number 2? Do we need to go over number 2? Yes? Okay. All right, so for number 2, this is a bit of a tricky one. The ball is moving up the hill, okay, initially. So its VI is going to be 3.0 meters per second uphill. Okay, 4 seconds later. This is like the worst thing that a question can do. How many significant digits are there in FOUR?
None.
I have no idea. That's not a measured value. It has to have been counted. Here's something I didn't tell you about significant digits. Counted numbers are supremely accurate. They have an infinite number of significant digits because you are 100% certain of your counting at all times. Okay, like if I watch a pendulum swing back and forth 4 times, I am 100% certain I counted to 4. Okay, so a counted number, because it isn't measured, cannot affect your significant digits. Okay, so FOUR means somebody went 1 1,000, 2 1,000, 3 1,000, 4 1,000. I counted 4 seconds. Okay, and we can't, they didn't measure it, they counted it. So it cannot affect the accuracy because it wasn't measured. Okay, it's dumb but true. Okay, so I'm just going to say time equals 4 seconds. Okay, and it's moving down the hill after those 4 seconds at 9 meters per second. All right, find the displacement of the ball. So again, I don't have to manipulate, but here's what I have to remember. VF is downhill. VI is uphill. So when I plug in my numbers, -9 plus 3 over 2 times 4. Okay, so -9 plus 3 is -6. -6 over 2 is -3. Okay, times 4 is -12. D is 12 meters downhill. This answer? Wrong. Question didn't give me positive and negative. Question gave me uphill. Therefore, my answer has to be downhill or uphill. Does that make sense?
Yeah.
Is that the same as up or down? Is up, down the same as uphill, down? It is not. Up or down is vertical, up or down. So if you have a hill question and you say the final velocity is down, that means you're falling through the hill. Okay? All right.
Maybe there's like a secret little rabbit hole.
A secret little rabbit hole?
Just like Alice in the
Okay, there's some like interdimensional
Yeah.
portal through which you can fall. Yeah.
Probably
Oh. If you can write that into the question somehow, I'll go for it. Most of the time, people just make the mistake of writing down instead of downhill. Okay, questions on how that formula works?
So you cast something wrong if I wrote down instead of downhill?
Absolutely.
Okay.
Yeah. In physics, we're very particular. Yeah. All right. Write this one down, and we'll walk through it in a minute. Okay, so this question's not only like an example of one of the formulas we're going to go over, but it's also an example of when you have to be mindful of the wording of the question for vector purposes. Okay, so golf ball is initially traveling at 25 meters per second. Did they give me a vector on that? They did not. Okay, so is that a velocity or a speed? Okay, so my initial speed is 25 meters per second. Okay, it hits a sand trap and slows down with an acceleration of -20 meters per second. This is worded terribly. If I slow down at -20 meters per second, what am I actually doing?
Backwards.
I'm actually speeding up.
Oh.
That's dumb. It's worded terribly. It should be slows down at 20 or accelerates at -20 meters per second squared. Okay, don't say both. That's like saying negative left is right. Okay, and yeah, I know you're gonna go, well, 2 wrongs don't make a right, Coderre. Yeah, but 3 do. Okay, no, that's not really true though. Don't believe that. But Okay, we got to make sure that we're understanding what a question is trying to tell us, even if it's telling us stuff that it shouldn't say. Okay, this is worded poorly. Okay, so we have to understand it is slowing down, and so our acceleration, yes, should be negative 20 meters per second squared. Okay, we want to find its displacement after 2 seconds. Okay, so I have a speed, I have an acceleration, which is vector. Okay, can I still find displacement? Technically, no. Okay, it just said it was moving at 25 meters per second and told me that the acceleration's negative. So I know it's slowing down. I'm not really calculating a displacement here. I'm actually calculating the distance. Okay, and that's, I know that's a little bit wishy-washy. Again, this is an example of a poorly worded question. Okay? No, because I'll make them up and I won't make mistakes like that. Okay? This is actually why we don't use the textbook that this stuff comes from.
What about like PATs and stuff, like, or diplomas?
No, those go through a pretty rigorous editing process, so no, you won't have to worry about that either. Okay, but we actually, when we first got these textbooks, Mr. Dickey and I were going through them, we're like, that answer's wrong, that answer's wrong, that answer's wrong, that answer's wrong. And we sent in our corrections, and they sent us back a corrections booklet. I kid you not, thing was 50 pages long. Okay? And they're like, so now you can buy the corrections booklet. We're like, we can what now? So you made a bunch of mistakes, printed the book without checking it, and now you want me to pay for the corrections booklet? Thanks, take textbooks. Okay, so, yeah. They actually ended up reprinting them, and yeah, they took the hit because that was dumb, and everybody did the same thing we did. Are you kidding me? No. Okay. So there's some wording like this that actually got corrected. Okay. So we've got this situation here. What formula am I going to use for this?
Would you have to modify the D equals VF plus VI?
Nope, because I don't have VF. What's a formula that has these 4 things in it? I might have to manipulate it, but it has these 4 things in it.
D equals VI plus 1 over 2 AT squared.
That one. Yep, I got time, I got VI, I got A, I'm looking for D. I don't even have to manipulate it, I can just plug in my numbers in this situation. So, VI was 25 times 2 seconds plus 1/2 times negative 20 times 2 squared. All right, so 25 times 2, I can't believe I just typed that in. Okay, plus 1/2 times negative 20 times 4. I'm not going to write 2 squared in. Okay, all right, so we got 10 meters. All right, now because they said displacement, and I can, kind of visualize this and know that the ball would have moved forward, I can say positive 10 meters. Okay, technically that would be a distance, but theoretically I can overlook it and see the situation.
2 questions. Why are we doing this if it's so stupid? If the question is so stupid.
Well, because it gives us the first example of the problem. Yeah. All right, what if I have to manipulate this thing? This one might be a little bit more involved. What if I want to solve for VI? Elliot?
I actually put my hand up for really something.
Didn't think it through? Okay.
Didn't think
Yeah. So it's like, ooh, oh no. Okay, think order of operations. Before I add these 2 things together, what do I have to do? I have to do all multiplication. So plus x. Can I subtract the whole thing?
But it's not in brackets.
Doesn't matter. Still order of operations. That is an operation I would do before I add it to this term here. Right? I would multiply these 2 things, I would multiply these 3 things, and then I would add them together.
So it doesn't matter as long as they're like together, they're like technically one, whether they have brackets or not.
As long as it would follow that according to order of operations, yes. Okay, so I can subtract that whole thing over to this side. D minus 1/2 AT squared equals VI times T. How do I get VI by itself?
Divided by
Divide by t. Okay, here's a mistake people make at this point. Ooh, there's t squared on the top and t on the bottom. I can cancel them.
No.
Nope, I can't. Okay, I can't cancel them because this operation has to go. It's a top divided by a bottom. That has to happen first. I can't calculate. Now, if these were all multiplied together, then could I cancel it? Yes. If it was d times 1/2 times 1 times a times t squared, then I could cancel the t's. Okay, but because there's a subtraction operation there, the t's will not cancel out. Tanya, question?
Can I use that?
Yes. All right, so that's how I would solve for VI. How would I solve for A?
When you divide by t squared,
Not yet. I will. I have to do something else first. What's not attached to A? VIT. Okay, again, think order of operations, right? This is a chunk, everything here is attached. This is a chunk, everything here is attached. Okay, so I gotta move what's not attached to A, which is this, first. So D minus VI times T equals 1/2 AT squared. Now,
divide by t squared.
and what else?
And 1/2.
Now I'm solving for A. Okay, just algebra, right? We just gotta, man, we haven't had to flex our algebra muscles very much yet. Okay, now we have to.
Oh, I guess not as a order of operations. I was about to say, couldn't you just say it d subtract VIT divided by just t? But then I realized that it's a multiplying. So
Right,
half.
multiplying, and T is squared,
So-
right? So I would have to do the exponent first, and then multiply, right? Okay, now here's the one that's super tricky. How would I solve for T?
When you subtract VIT and divided by 1/2 and times a square root.
But then I've still got T, right? T is in two places, okay? So the good news here is you'll never have to use this formula to solve for T unless VI is 0. Because you would have to factor it, okay? And we can't guarantee that you've taken Math 20, where you learn how to factor and do the quadratic equation and all that other stuff that I barely remember, okay? So unless VI is 0, you won't have to use this formula to solve for T. If VI is 0, what's VI times T?
0.
Right, so could you solve for T now? Yes, okay? But being that if VI isn't 0, there's actually a number there, okay? You would have to factor it to get T by itself, okay? So you're not gonna be asked to do that. All right. Try those two, they use that formula. Yeah. All right, so for the first one, skiers moving down a uniform slope at 3 meters per second. Okay, if the acceleration down the hill is 4 meters per second squared, okay, find the skier's displacement after 5 seconds. Okay, I don't have to manipulate, I just have to plug in VI times T plus 1/2 AT squared, because those are the things that I have. Okay, so we'll have 3 times 5 plus 1/2 times 4 times 5 squared. Okay, and that should give us our 65 meters downhill, not down. Okay, once again, and it's wrong. Okay, downhill, not down. Okay, ready for number 2? What do we have to do in number 2? Yeah, we got to convert kilometers per hour into meters per second, and then the minute into seconds. All right, so there's a number of conversions that have to happen in that one. So 100 kilometers per hour divided by 3.6, 27.7, repeating? Okay, meters per second, and they just say it's on a flat road, so that's a speed, okay, not a velocity. Applies the brakes at 0.8 meters per second squared. What do I have to remember about that number? It's negative. Last time I checked, thankfully, the brakes make you accelerate backwards, not forwards. Odd that we call only one of the pedals an accelerator. Think about it. They both cause acceleration. One should be called the negavator. Brake, I know brake is better.
I mean, technically all three. Like if you drive standard, like if you
Yeah.
let up your clutch a little bit, you'll move forward. So technically. like,
Well, and if you
all
just press
three
in the
of them-
clutch, you'll start slowing down.
Yeah. So all three of them are technically accelerating.
We're gonna run out of names. They're never gonna catch on because they already have names. Okay, so then we got 1 minute, so a time of 60 seconds. Okay, how far did the motorcycle travel during this time? So I'm looking for D, and this time I'm looking for a distance. I'm not gonna put a vector on this. Okay, they didn't give me enough vectors, so I'm actually solving for a distance here. So D equals VI times T plus 1/2 AT squared. So our 27.7 times 60 plus 1/2 times negative 0.8 times 60 squared, okay, should give us 2.3 times 10 to the 2 meters, or 230 meters during that time. Okay. All right, how are we feeling about the acceleration stuff so far? Okay. Tomorrow, we're going to do two things. Tomorrow, we're going to go through your vector assignment. Okay, so I'll hand them back, and we'll go through it in its entirety. And we're going to do the last two acceleration formulas. Okay, Monday, we'll work on acceleration. Tuesday, probably do a lab on acceleration. Wednesday, finish up acceleration. Thursday, start projectile motion. And a week from that day will be your unit exam, October the 6th. Okay? If that date changes, it will only change forward. Okay? I will not make it earlier than October the 6th. It will be October the 6th. More than likely, that's the day of the week. If I have to bump it back, I will bump it the right way. Okay? All right, we'll call it there.